Hello friends, welcome back to my YouTube channel. Today I'll be talking about the Q line or the feed line. So this would be a part of my discussion on the McCabe method, which I have been doing since last few videos. And this again is part of my discussion on distillation. This will be 27th part of my discussion on distillation. So today I'll tell you what is the Q line, which is also called the feed line. I will be deriving the equation for the Q line, and you'll also know what is the Q line. Okay, so let us start the discussion. To begin with, we will revisit the concept of the parameter Q. Parameter Q, as you know, it gives a thermal condition of the feed. I have discussed in detail about this parameter Q in my earlier videos. You please watch those videos. I'm giving link to those videos in the description section. So the parameter Q, it gives thermal condition of the feed. It is defined by this mathematical equation. Q is equal to Hg minus Hf divided by Hg minus Ha. In this case, Hg is the molar enthalpy of saturated vapor. Molar enthalpy of saturated vapor. Then you have HF. HF will be the molar enthalpy of feed, and HL will be the molar enthalpy of the liquid phase. Okay, so you have this equation which is used to define the parameter Q, Hg minus Hf divided by Hg minus HL. If you look at the numerator, in the numerator you have this term Hg minus Hf. It is difference between the molar enthalpies of the feed and the saturated vapor. So this is nothing but the heat required to convert 1 mole of feed from its initial conditions to saturated vapor. So whatever heat is required to convert one mole of feed from its initial condition to saturated vapor is given by this term Hg minus Hf. And when you look at the denominator, which is Hg minus HL, which is the difference between molar enthalpies of the liquid phase and the vapor phase. So this is nothing but molar latent heat of vaporization. So as per this equation, Q is the ratio of these two quantities. Okay, so that's why you can define the parameter Q as ratio of heat required to convert 1 mole of feed from its initial condition to saturated vapor to the molar latent heat of vaporization. Or you can define it like the heat required to convert 1 mole of a feed from its initial condition to saturated vapor. And in the denominator, divided by the molar latent heat of vaporization. Okay, so the definition goes like this. The heat required to convert 1 mole of feed from its initial conditions to saturated vapor divided by the molar latent heat of vaporization. I have discussed in detail about this equation. Rather, I have derived this equation in my previous videos on this topic. You please go and watch those videos. Okay, so let us continue. There is another definition for parameter Q, which again I have discussed in my earlier videos. So you can define the parameter Q using this equation as well. What is that equation? Q is equal to L bar minus L divided by F. So L bar, in this case, L bar is molar flow rate of the liquid phase in the stepping section. So you must be remembering, when you have the column and the feed plate, then the feed plate divides the column into two sections. The section above the feed plate is a rectifying section, and section below the feed plate is stepping section. Okay. So L bar, it represents molar flow rate of the liquid phase in the stepping section. And L will be the molar flow rate of the liquid phase in the rectifying section. So if you have to show this over here, so you have liquid coming from the top in the rectifying section, it will have molar flow rate of L, and then you will have the liquid that is going to the stepping section. So after it comes into the stepping section, the flow rate will be changing to L bar. Okay, and F is the molar flow rate of the feed. Molar flow rate for the feed. What is molar flow rate? Molar flow rate, for example, will have unit of kilomole per second, moles per unit time. Okay, so as per this definition, you can define Q, or as per this equation, you can define Q as the moles of saturated liquid resulting in the stepping section per mole of feed that enters the column. Okay, so for every 1 mole of feed that enters the column, what is the moles of saturated liquid that will be resulting in the stepping section? And that moles of saturated liquid is nothing but Q. Okay, so the moles of saturated liquid resulting in the stepping section per mole of feed that enters the tray column. Again, I have discussed this definition in detail in my earlier videos on this topic. Okay, so you have two mathematical equations that can define the parameter Q. Parameter Q, it gives the thermal condition of the feed. Okay, so let us continue. Then let us know, as we said, as we understood, values of parameter Q will tell you about the thermal condition of the feed. So for various types of feed to a typical tray column, let us know what are the values for parameter Q. I have talked about it in my earlier videos. This is just a simple, small revision of that. So let us first list the types of feed to a typical tray column. So one type is the feed could be a cooled liquid, then it could be a saturated liquid, or it could be a partially vaporized feed, or it could be saturated vapor, and it could be superheated vapor. Okay, so you have these 5 types of feed. You have cold liquid, it could be cold liquid, it could be saturated liquid, it could be partially vaporized feed, it could be saturated vapor, or it could be superheated vapor. Now let us briefly know more about each type. So cold liquid is nothing but a liquid solution at a temperature well below its bubble point. So when you have feed as a liquid solution at a temperature that is well below its bubble point, then we call that feed as cold liquid. And for cold liquid, the value of Q is greater than 1. Then what is saturated liquid? Saturated liquid is a liquid solution at its bubble point. A liquid solution at a temperature which is equal to its bubble point. And for saturated liquid, the value of Q is 1. Then partially vaporized feed, it is a mixture of liquid and vapor phases. So some part of the feed is vaporized, while the remaining part is in the liquid state. So partially vaporized feed is nothing but a mixture of liquid and vapor. And for this type of feed, Q will be less than 1, or to be more correct, Q will be between 0 and 1. And then fourth type is saturated vapor, which is nothing but vapor at its dew point. And for such a feed, Q is 0. Then you have superheated vapor, that is a vapor which is at a temperature above its dew point. For such feed, Q will be less than 1. Okay. So one way of understanding Q is Q tells you about the liquid portion of the feed. Okay. So at the end, we have understood, or now we know what are the various values of Q. For cold liquid, Q is greater than 1. For saturated liquid, Q is equal to 1. Saturated liquid will also be understood as a liquid solution at its oval point. Then for partially vaporized feed, Q is between 0 and 1. For saturated vapor, Q is equal to 0. And for superheated vapor, Q is less than 0. I have discussed how these values are obtained in my earlier videos. You please go and watch those videos. Okay, now let us continue further. Now let us know what is the Q line, or this is also called the feed line. So what is this? It is the locus of intersection of operating lines on the XY plot. Operating lines, by that I mean operating lines for the rectifying section and the stripping section. Okay, so when this operating lines are plotted on the XY plot, they will be intersecting with each other. And as their slope changes, the intersection point will be changing its position. So this locus of the intersection point is nothing but the feed line or the Q line. Okay, so how it is understood? The Q line is nothing but the locus of intersection of operating lines on the XY plot. Locus is, you can understand it as collection of the intersection points. So as the slope of the two operating lines is going to change, the intersection point, their intersection point will be moving. Okay, so that collection of all possible intersection points will be the Q line. Okay, so that's why we are understanding it like the Q line is the locus of intersection of operating lines on the XY plot. If someone asks you to define Q line, you can define in this way. The Q line is the locus of intersection of operating lines on the XY plot. Which operating lines? Operating lines of rectifying section and the stripping section. Okay. Now over here I mentioned the XY plot. Now let us briefly understand what is the XY plot. So it is a graph that is obtained by plotting vapor liquid equilibrium data, which is simply called VLE data. So when you have VLE data and when you plot it, the resulting graph will be the XY plot. Okay? So let me tell you more about it. What is VLE data? VLE data is nothing but a collection of pairs of X and Y that are in equilibrium with each other. Okay, a collection of values now x and y that are in equilibrium with each other. What is x? X is nothing but mole fraction of the more volatile component in the liquid phase. So more volatile component, a component which will be having a lower boiling point and higher vapor pressure. Okay. And y, what is y? Y is mole fraction of the more volatile component in the vapor phase. So when you have liquid and vapor phases that are in equilibrium with each other, and when they are in equilibrium with each other, if you measure the concentration of more volatile component, so for example, you have a liquid phase in equilibrium with vapor phase. Okay. So when they are in equilibrium with each other, and you measure the concentration here will be described in terms of mole fraction, the more convenient way of doing that. So X will be mole fraction of the more volatile component in liquid phase. Y will be mole fraction of the more volatile component in the vapor phase. Okay. So now when you have this pair, it will be a pair of equilibrium concentrations, equilibrium mole fractions. Okay. So VLE data is collection of many such pairs. When you have another equilibrium state, let us say where liquid L1 is in equilibrium with vapor V1, and then you'll have particular concentration in the liquid phase, let it be X1. We'll have concentration in the vapor phase, let it be Y1. So now this pair will also be equilibrium mole fractions or equilibrium concentrations. So that's why I'm saying VLE data is nothing but a collection of pairs of X and Y that are in equilibrium with each other. Such X and Y's that are in equilibrium with each other. Okay, so X is the mole fraction of the more volatile component in the liquid phase. Y is the mole fraction of the more volatile component in the vapor phase. Okay, so how this XY plot is obtained? So for doing that, X is plotted on the X-axis and Y is plotted on the Y-axis. Mole fraction in the liquid phase is plotted on the X-axis and mole fraction in the vapor phase, it is plotted on the Y-axis. Okay, so let us continue. So if you have, now let us understand how Q line will be existing on the XY plot. So XY plot, we are going to plot X on the X-axis, that is mole fraction of the more volatile component in the liquid phase, and then Y on the Y-axis. So this would be the diagonal line I'm using for the reference. So there is a square plot where scale on the X-axis and on the Y-axis that is same. So it would be a square plot. And now I have drawn the diagonal line which will be used for the reference. The actual plot will be, as I said, this is the diagonal line and the actual plot will be this curve, and this curve is nothing but the equilibrium curve. Okay. Then operating line for the rectifying section, how to plot it, I have discussed in one of my earlier videos. Please watch those videos. So for the rectifying section, the operating line will have this equation: yn plus 1 is equal to r upon r plus 1 into xn plus xd upon r plus 1. Again, I have derived it in my earlier video, one of my earlier videos. For how the line will be plotted, so you have to locate xd. The operating line will start at xd at this point. This point will have coordinates of xd. which is intersection of the operating line for rectifying section on the diagonal line, and it is having an intercept of xd upon r plus 1. So this would be xd upon r plus 1 intercept on the y-axis, and line joining these 2 points xd and xd upon r plus 1, that is nothing but the operating line for rectifying section. Okay, then for stripping section, the equation for the operating line is m plus 1 is equal to L bar m divided by L bar m minus w into xm minus w upon L bar m minus w into xw. Again, I have discussed it in detail in my earlier videos. Okay, so how is this line, the operating line for the stripping section, plotted? So you have to locate xw, go to the diagonal. So this point will have coordinate of xw. That means this point has coordinates of xw, and the operating line for the stripping section will be starting over here. Okay. For time being, for the purpose of understanding, I will show a stripping section line. Okay, so you'll come to know that the two lines, operating lines for the two sections, have intersected at this point. Okay, so as their slope changes, this intersection point is going to move. So let me show you. But over here, the intersection point is over here. As the slope of these two lines change, this intersection point may be moving like this. This is just an example. It can move in other directions also. For your understanding, I am showing that let the intersection point moves like this. Okay. Then the Q line is collection, locus of all this intersection points. So the Q line will be a line that will be passing through this intersection points. So this will be the Q line. Okay, so over here, the way I have shown the Q line, it may change depending on the type of the feed. You will be understanding it in our future discussions. Okay, so this is the Q line. So this is how Q line is present on the XY plot. So it shows how the two lines, how the two operating lines are intersecting with each other, how and where they are intersecting on the XY plot. Okay, so we are going to get the equation for this Q line in today's discussion. Okay, so I hope this is clear to you. If you have any doubt, you please mention that in the comment section. Okay, now let us move further. Again, quickly we'll know about the tree column, because we need to take material balance. In order to get the equation for the Q line, we need to know the material balance. So let us quickly know about the tray column. So you have a cylindrical vessel. You have number of trays in the cylindrical vessel. Then the plates or trays are numbered in this way. The topmost tray is the first plate, and the bottommost tray is nth plate. Feed is entering on a plate in the column. We call that plate as the feed plate. I will talk about the notations shortly. And then I have numbered randomly plates in the column. So this is nth plate, this is mth plate, and this is the plate next to mth plate is m+1 plate. Okay, so after feed enters into the column, the liquid portion will be flowing down. It will be taken out at the bottom. Then it will be sent to a reboiler where heat will be added to create the vapor phase. The resulting vapor phase will be admitted into the column at the bottom. Vapor phase will rise. It will be taken out at the top, sent to a condenser where heat will be removed from it to get a condensate. Condensate will be divided into two parts. One is taken out as the top product or distillate. I'll talk about the notations. And the other portion of the condensate is sent back to the column as reflux. And we'll know more about it. After the reflux enters into the column, it will be flowing down. And on the feed plate, it will be joining the feed. Okay, so from the reboiler at the bottom, you are taking out the residue or the bottom product. Then feed plate is dividing the column into two sections. The section above the feed plate is rectifying section, and section below the feed plate is stripping section. I have discussed many times how the column operates. Now you must be expert in telling how the column operates. Okay, now let me talk about the notations. You have the feed solution. Feed solution, let us say that it is a binary liquid solution of two components, component A and B. Out of this two, A is the more volatile component, that is A is having a lower boiling point and a higher vapor pressure. F is the molar flow rate of the feed. XF is mole fraction of the more volatile component in the feed. That is mole fraction of A. E is the more volatile component. Then you have the distillate. For distillate or the top product, D is its molar flow rate, and XD is mole fraction of A in the distillate. That is mole fraction of more volatile component in the distillate. Okay. Then you have the residue. For residue or the bottom product, W will be its molar flow rate. XW will be in the mole fraction of A in it. And the reflux stream, over here, you have L0, the molar flow rate for the reflux, and then you have XD, the mole fraction of more volatile component in the reflux will again be XD, because over here there is simple division of the condensate. No composition change is involved in that. So that's why reflux, composition of reflux or mole fraction of the more volatile component in reflux will also be XD. Okay. Then you have the reboiler. In the reboiler, you are adding heat, and QR represents the rate of heat addition. And in condenser, you are removing heat, and the rate of heat removal is QC. Today, in this particular discussion, we are not dealing with energy balance, but I have just mentioned what are the notations that are being used. Now let us move further. Now what we will do, first we will consider the entire column. What is the task? The task is to take material balance, total material balance, and material balance for the compound, more volatile component. In this case it is E. So we are going to use three, you can say, parts. One is we will be using the entire column. Then we will be using the rectifying section. And finally, we will be using the stripping section. Okay, so I'm showing the entire column. And if this is to be represented, so now the entire column is considered. And now you can easily understand what are the material streams that are going into it and what material streams are coming out of it. So one is you have the feed stream that is going into it, into the envelope. And then you have the distillate stream that is coming out from the envelope. You have the residue that is coming out from the envelope. So these are the material streams. Whereas QC is coming out of the envelope, the energy stream, and QR is going into the envelope. As I told you, we are not going to consider that for here. Okay, so now the entire column, I am showing it by a simple, you can say a block. The block diagram would be like this. So feed is entering. It will be having this parameters associated with it, FXF. Then distillate will be coming out at the top, DXD. I have just told you what are this. And at the bottom, you are taking a residue, WXW. Okay. Now, the task is simple. We are going to consider material balances, total material balance and the material balance for the more volatile component. So, if you have to write total material balance, again, we are going to write total material balance under steady state conditions, where you have input material is equal to output. The rate at which material comes into the column is equal to rate at which it goes out of the column. Okay. So over here, the material comes with the feed and it goes out with distillate and bottom product. So simply it will be F is equal to D plus W. So whatever material comes in the column, it goes out along with the distillate and then along with the residue. I'm calling this as equation number 1. Then material balance for E, that is more volatile component. So in feed, it will be total flow of feed into fraction of E. So FXF, that is equal to DXD plus W into XW. I'm calling it as equation number 2. Okay. Now, after considering the entire column, let us concentrate on the stripping section. So for that, I'm going to use an envelope to show the rectifying section. So rectifying section, if you look at the diagram, you have this liquid stream that is coming out of the envelope that we have considered. This vapor stream that is going into the column, into this envelope, and you have this material stream, and that will be the third one, the distillate stream that is coming out of the envelope. So if you have to represent it with the help of this block diagram, so you have stream number 1 that is coming out. So we are going to denote it as the liquid flow from this will be ln XA and mole fraction of A in it will be XA. So this represents liquid molar flow rate of the liquid that is coming from N plate. Then at the top, distillate stream is coming out. So it will be DXD. And at the bottom of this block, vapor stream is going in it, and it is coming from the next tray next to nth plate, which is n plus 1 plate. So it will be Gn plus 1 into Gn plus 1 will be it will be G bar n plus 1 since it is we are discussing rectifying section. So it is coming from n plus 1 plate. So that's why it will be having flow rate of Gn plus 1. And mole fraction of A in it will be yn plus 1. Okay, so again, the total material balance at steady state, it will be Gn plus 1 is equal to Ln plus D. So Gn plus 1 is equal to Ln plus D. And I'm continuing my numbering. This will be equation number 3. And then you take material balance for E, that is the more volatile component. So it will be simply Gn plus 1, Yn plus 1. Gn plus 1 into Yn plus 1, that is equal to Ln into Xn plus D into Xt. And let us call this as equation number 4. Okay. After taking balance for considering this rectifying section, now let us consider the stripping section. So first, let me show you the stripping section. So you have the entire column, and now I am considering this part of the stripping section. So for this envelope, you have this material stream, the liquid stream that is coming from nth plate, and then you have this vapor stream that is coming or that is rising from m+1 plate, and finally you have the residue stream, which is and the third material stream associated with this envelope. Okay, so let us now simply show it by a block diagram. Okay, so from the top you have the liquid stream that is coming from nth plate. So this will be, the flow will be L bar M and mole fraction will be XL. So bar indicates that now we are in the stripping section. And at the bottom you are taking the residue or the bottom product, and the vapor stream that will be coming out of this, the section that we have considered, will have molar flow rate of G bar M+1. It is coming from M+1 plate, so that's why G bar M+1, and accordingly mole fraction for A in it will be pi M+1. Okay, so again we will write the total material balance at steady state. It will be simply L bar M is equal to G bar M+1 plus W. So L bar M is equal to G bar M+1 plus W. Let us call this as equation number 5. And then we will be writing material balance for E. It will be simply L bar M into XM, that is equal to G bar M+1 into YM+1 plus W into XW. So L bar into XM, that is equal to G bar M+1 into YM+1 plus W into XW. And now I'm calling this as equation number 6. Okay, so let us move further. Now, again, we will now get the equation for the Q line. So for that, let us collect. We have now 6 equations. I will collect all those equations over here. So for entire column, the total material balance is F is equal to T plus W. That was equation number 1. Then material balance for component A, which is FXF is equal to DXT plus W into XW. Equation number 2. Then for rectifying section, you have total material balance as Gn plus 1 is equal to Ln plus D. Equation number 3. Then material balance for more volatile component Gn plus 1 into Yn plus 1, that is equal to Ln Xn plus D XD. Equation 4. Then for stripping section, you have the total material balance L bar M is equal to G bar M plus 1 plus W. Equation number 5. And then you have L bar M into Xm, that is equal to G bar M plus 1 into Ym plus 1 plus W into XW, and this is equation number 6. Okay. Now we are going to use one of the assumptions of the McAfee method. What is that? Equimolar overflow and vaporization. So as per this assumption, molar flow rate of liquid phase in the rectifying section is constant throughout that section, and same applies for stripping section. That is, in the rectifying section you have L1 is equal to L2 is equal to L3, that is equal to L. That is molar flow rate on K1, K2, K3, they are equal, and we are going to denote that by L. Similarly, in the rectifying section, for vapor flow also, you will have G1 is equal to G2 is equal to G3, and we are going to denote that by G. In stripping section, likewise, you have L bar 1 is equal to L bar 2 is equal to L bar 3, that is equal to L bar. And then G bar 1 is equal to G bar 2 is equal to G bar 3, that is equal to G bar. This is as per assumption, one of the assumptions of McAfee method, simplifying assumptions. Liquid flow, same throughout a section. Vapor flow, same throughout a section. Okay, so we are going to use it. Now, I hope you have understood it. Now, I'll erase it so that other equations can be written over here. Okay, so the assumption now is clear to you. We are going to use that. Okay, so if I use it, and now you look at equation number 3. So I have used the assumption in equation number 3. Now there is no subscript involved. And the balance is simply G is equal to L plus T. Let us call it as equation 7. Similarly, for equation number 4, now will be written as G into Yn plus 1 is equal to L into Xn plus D into Xd. And now we will be calling it as equation 8. Then for stepping section, it will be L bar is equal to G bar plus W. And which I will rearrange it like G bar is equal to L bar minus W. And I will call that as equation number 9. And the material balance for component L bar M into Xm, that is equal to G bar into Ym plus 1 plus W into Xw. Again, I am rearranging it. I am writing G bar into Ym plus 1 is equal to L bar into Xm minus W into Xw. And I am calling it as equation number 10. Okay. So I'll be performing this too. First, I will subtract equation 8 from equation 10. So one task is equation 10 minus equation 8, and the other task is equation 9 minus equation 7. Equation 9 minus equation 7 and equation 10 minus equation 8. So let us do it. So for that, we will consider again, we will consider the equations. So you have equation 7, which is G is equal to L plus T. Then you have Y into N plus 1 is equal to L into Xn plus D into Xd, equation 8. And then you have G bar is equal to L bar minus W, equation 9. And G bar into Ym plus 1 is equal to L bar into Xm minus W into Xw, equation 10. Okay, so I have collected the required equations over here. We have got these equations just now. So let us perform this task. Equation 10 minus equation 8. Right hand side terms will be subtracted and left hand side terms will be subtracted. So equation 10, on the right hand you have G bar Ym plus 1, G bar into Ym plus 1 minus G into Y. Just a minute. So you have G bar into Ym plus 1 minus G into Yn plus 1. The left hand side of the two equations now are subtracted. Then you have that is equal to L bar M into Xm minus Ln into Xn minus W into Xw minus D into Xt. Okay. So we have subtracted this term, or we are subtracting this term from this term. So you get this. Okay. Now let us do some rearrangement. What is that? Let me tell you. On the feed plate, what happens? Feed plate, since it divides a column into rectifying and stripping section. So for that, for this reason, on the feed plate, there will be no such M plus 1 subscript. So it will be simply mole fraction of the more volatile component in the vapor phase. Let us denote it as Y. And you have Xm is equal to Xn. That is X. We are going to assume it as X, mole fraction of more volatile component on the feed plate. Okay, so next would be, we will be replacing this Ym plus 1 and Yn plus 1 with simply Y and Xm and Xn with X. since we are on the same plate now, the feed plate. Okay, so if you use that, this particular equation will now be transformed to this form. G bar into y minus G into y, that is equal to L bar into x minus L into x minus W into XW minus D into XD. Okay, so G bar into y minus G into y, that is equal to L bar into x minus L into x minus W into XW minus D into XD. Okay, so after using assumption of equimolar overflow and vaporization, and then knowing that on the feed plate the compositions will now be denoted as x and y, so you get this equation. Okay, so now in the next step what we will do, we'll take y common from on the left hand side, so it will be G bar minus G into y on the left side. Then on the right side, from these two terms, we are going to take x common. So it will be L bar minus L into x. And then in the remaining part, we will be taking the negative sign common. So it will be WXW plus D into XD. Okay. So that completes our first task, where we have subtracted equation 8 from equation 10. Now let us perform the second task. Second task is equation 7 will be subtracted from equation 9. So it will be G bar minus G is equal to L bar minus L minus W minus D. That is G bar minus G is equal to L bar minus L. And over here you can take the negative sign common. So it will be minus W plus D. Okay. So let us continue with this. Okay, again we are discussing the equation of the Q line. So previously we got this equation, G bar minus G into y is equal to L bar minus L into x minus W into XW plus D into XD. Let me call this as equation 11. And then we also got G bar minus G is equal to G bar minus G is equal to L bar minus L minus W plus D, and I'm calling it as equation 12. Okay, so now what will we do? We will use equation 12 in equation 11. How? We will be replacing G bar minus G with this term. So if we do that, we'll be getting L bar minus L minus W plus D. Now we have replaced G bar minus G into y, that is equal to L bar minus L into x minus W into XW plus D into XD. Okay. So now just remember what equation 1 and 2. Equation 1 is F is equal to D plus W. So we can use that over here. And equation 2 is Fxf is equal to dxd plus wxw. So we can use over here. Okay, so when you use it, you get the resulting equation. So we are going to use equation 1 and 2 in equation 13. So you get L bar minus L minus F into y, that is equal to L bar minus L into x minus F into xf. Okay, now let us continue with this equation. So we have got this equation just now, L bar minus L minus F into y, that is equal to L bar minus L into x minus F into xf. Now the factor Q is defined by this equation. At the beginning we understood Q is Q L bar minus L upon F. So that means L bar minus L is Q into F. So my next task will be, I will be replacing L bar minus L in equation 14 with Q into F. So if I use it in equation 14, it will be QF minus Q into Y is equal to QFX minus F into XF. So you must have noticed Now we have replaced L bar minus L with QF. Okay. So now you have F common everywhere on the right side and then on the left side. So it can be removed. So if we do that, before that, I have used this step where I have taken F common. So it will be Q minus 1 into F into Y. And on this side, nothing will happen. Q into F into X minus F into X. And now this F will get cancelled. So you are left with Q minus 1 into Y. That is equal to QX minus XF. And which when rearranged will give us this equation. Y is equal to Q upon Q minus 1 into X minus XF upon Q minus 1. So this equation is an equation of a straight line. And for this line, the slope of the line is, this equation is of this form. Y is equal to mx plus c. Okay. So slope of the q line, this straight line is nothing but the q line. So slope of the q line will be q upon q minus 1, and intercept on the y-axis will be minus xf upon q minus 1. So this will be the intercept. So c will be minus xf upon q minus 1. So this straight line is nothing but the q line or the feed line. Okay. So this is how you get the equation for the q line. The steps to be followed in order to get to this equation I have discussed, and I hope you have understood those steps. If you have any doubts, you can mention that in the comment section. Okay, so thanks for watching my video. I hope now you know what is a Q line. It is also called feed line. How to get equation, how it is plotted on the XY plot, and what is its equation. How it is plotted, I have just told you the general way of doing that. How exactly it will be looking for each of the feed type, I will discuss in my future videos, in my next video. Okay. So for time being, thanks for watching my video. I hope you are understanding what I'm talking about in my discussion. Okay, so thanks for watching. Do subscribe to my YouTube channel. Please tell your friends to subscribe to it. There are many things coming on this channel regarding chemical engineering. It is not only confined to distillation, not only confined to mass transfer. So I'll be discussing various aspects of chemical engineering that will be useful to you as chemical engineers. Okay, so thank you. Have a nice day. Hope to see you soon in my next video.